Section 7.6, tree diagrams. So when you're looking at a tree diagram, the reason why they call it a tree diagram is because I guess it looks like branches of a tree. By the time it gets all done, you could end up making it look like that. So that's why they call it a tree diagram. What you're looking at is independent events. Now, independent events means that the first event does not impact the second event. Okay, so there has to be for independent events for this one. So, for example, if I flip a coin, I have two possible things that I could get. I could get a head, or I could get a tail. Now, after I flip my coin, let's say I get a head. What are my possibilities that I could get with one of these one die? Well, I flip a head and then I roll this die. It doesn't matter that I flip this. It's not going to affect what happens to this. So I could get a 1. I could get a head and a 2, a head and a 3, a head and a 4, a head and a 5, or a head and a 6. So that's my possibilities I could get when I get a head. Let's say I've gotten a tail, though. What could I get? Well, I could get exactly the same thing. So I could end up with, and I'll just copy and paste the whole works of it on there again. So I could end up with a tail and a 1, a tail, then I could get a 2, a tail and a 3, a tail and a 4, a tail and a 5, or a tail and a 6. So these are the possibilities or the outcomes that I could end up getting. So I'm going to put my outcomes, I'm going to write them all out here so I know exactly what I could have gotten. So I follow it kind of like a, almost like a pattern, I guess. Head and a 1 is my first outcome. So I'll put that right directly across from this. A head and a 1 I could have gotten. I could have got a head and a 2. Could have got a head and a 3. Could have got a head and a 4. I could have got a head and a 5. Or I could have got a head and a 6. And I'll try to keep them across from each one. If you have a bit more time, you can make it even neater. So I'll move this down again. So now I'm going to see what I could have gotten if I gotten a tail first. I could have got a tail and a 1, a tail and a 2, a tail and a 3, a tail and a 4, a tail and a 5, or a tail and a 6. So all together, I could have gotten 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible outcomes. So 12 possible outcomes if I flip a coin, and then I roll a die. Okay. So you can calculate then what are your chances of getting a head. Well, it's going to be 1, 2, 3, 4, 5, 6 out of 12. What are my chances of getting a head and a 1? Well, this is the only one that's a head and a 1, so that would be 1 chance out of 12. What are my chances of getting a head and an even number? So I would say a head and an even number. I could say, oh, this is a head and an even number, this is a head and an even number, and this is a head and an even number. So there's 1, 2, 3 chances out of 12 that it'll be a head and a even number. Usually when you write your probabilities, you need to write in a format like this, P for probability, and then if it's a head and even number. And then, of course, your bracket at the end, and you put an equal sign. And what did we say for head and an even number? I believe it was 3 out of 12. And sometimes you might be asked to reduce your fraction to a lowest possible fraction. In other words, you could divide 3 by 3, and you could divide 12 by 3, because 3 goes into 12. So that would reduce your fraction to 1 over 4, or 1/4 of a chance. Now again, you can change that 1/4 of a chance to something out of 100. That would be timesing it by 25. So you'd have 25 out of 100, which is 25%. So using what we learned on previous lessons, the one before this, you could actually figure out what your fraction is, and then you could change it to a percent if you wanted to, if you were given a percentage. Okay? Now that is a theoretical probability. In other words, in theory, that's what you should end up with. But we all know in real life the coin does not land on heads half the time always. Some people are luckier than others. They pick heads all the time and they end up usually winning. And other people, for whatever reason, they pick tails and they always win with tails, or they can never win a coin toss. So you'd think you'd win a coin toss at least half of the time, but in real life or in experimental probability, it doesn't always work out that way. So let's look at a example here. It says a popular game at a winter carnival is a spinner game called Tropical Orange. To play the game, a player spins the pointer on each of the spinners. So here's your two spinners. A player must get red on one spinner and yellow on the other spinner, because red and yellow make orange. Okay? So we're going to play the game at least 40 times and record your results. So when you play the game 40 times and then record your results, you're going to end up with 40 actual outcomes. So there you go, COMES. So your outcomes will end up being 40 of them written down, and then you'll end up getting maybe, I don't know how many times, we're going to calculate it in a minute. You might end up getting violet and red for the first one. You might get yellow and orange, or yellow and red for the next one, and you might get a few times you might get yellow and red. So you'd list all your outcomes and then see how many times out of 40 you get each combination that you have. Now, what we're going to do is calculate, you could calculate the theoretical probability of making orange. Okay? But we're going to make a tree diagram to list the possible outcomes first. So making a tree diagram is not too hard for this one. Let's look at our first possibility. We've got two spinners. So first we're going to do spinner A. Then we're going to do spinner B. And then we're going to do, then we're going to see how many times we get the outcomes, or what we're looking for. So for spinner A, what are our four possibilities? Well, if you look back, there's violet, yellow, blue, and red. So V, Y, B, and R. So I'm going to put violet, and give myself some space, blue, yellow, and of course, red. So that's my four possibilities for spinner A. Of course, if we get a violet and then we do spinner B, what is our four possibilities for spinner B? Well, if we look back at it, spinner B has exactly yellow, red, red, and yellow. So we're going to go back here and go, you could have gotten yellow, you could have gotten red, you could have gotten red again, and then, of course, the other one I believe was yellow. Like that. Okay, so that's our possibilities that we could have gotten. Now, if we had gotten blue at the first one, we still could have gotten yellow, red, red, or yellow for the second one. So what I'm going to do to save myself some time, I'm just going to copy that and paste it for my four possible outcomes for B. And I'll move it down. See, sometimes you need a little bit of extra space here to write these. There we go. I'll just move them down so I got some space. So if I got blue, I could have also gotten yellow, red, red, and yellow for my second spin. Again, for if I got yellow on my first spinner, I could have also gotten yellow, red, red, and yellow on my second spinner. If I got red on my first spinner, I also could have got yellow, red, red, or yellow on my next spinner. So now I've written all my possible things I could have gotten, all my possible outcomes. Okay, continuing with this one. Now that we've figured out what our all possible outcomes will be, all we have to do now is write out what we could have gotten. So start with V. You could have gotten violet and yellow. You could have gotten violet and red. You could have gotten violet and red. And you could have gotten violet and yellow. So I do that for each one of these. Blue and yellow, blue and red, blue and red, and blue and yellow. I do it for this one, yellow and yellow, yellow and red, yellow and red, and yellow and yellow. And then I go down here, I could get red and yellow, red and yellow, red and red, red and red, and red and yellow. So if I add up what my possible outcomes are, I would have 16 possible outcomes. So it's a total of 16 outcomes. And the question here asked us, what's the theoretical probability of making orange? So which colors make orange? You must get red and yellow to make orange. So let's circle all the red and yellow ones. So there's red and yellow. Nope, these are all violets. This is blue and yellow. Nope, we need red and yellow. So we got yellow and red. Here it is, one of them. Yellow and red. And, oh, there's red and yellow. And there's red and yellow. So there's how many? We've got 1, 2, 3, 4. 4 chances out of 16 that it'll be red plus yellow, which is orange, of course. Okay. So we got a 4 in 16 chance that it'll be orange. Theoretically, that's what it should have worked out to. Now, of course, 4 out of 16, if you divide the top by 4 and you divide the bottom by 4, you end up with 1 over 4, or 1/4 of a chance. Of course, 1/4 is 25%. If you change it to, there we go, if you change it to percentage. So, what's the rule for making a tree diagram? You figure out what your first object is. If it's a spinner, you see how many parts it has. If it has 4 different colors, then you have 4 different colors written out. If it only had 2 different colors, you would only have 2 colors written out. Then you look at the next thing that you're spinning or rolling or whatever. And if it has 4 possible outcomes, you write, like a tree, branches, you write down the 4 possible outcomes for each of the previous outcomes. So you've got to write the same ones for connected to violet, the same ones connected to your other one, and so on. Then your final step is to just kind of follow them, like violet and yellow, and then write it right across from each other. Then you go violet and red. You don't have to circle it, but violet and red, and you write it right across from each other like that. So you're listing out your outcomes so that you know theoretically what it could work out to. So that's the easiest way to do that one. So I would calculate, you could do it experimentally, which means you could actually do the experiment and see what you ended up with 40 times, or you could calculate it based on theory. Okay. There is one last one. It says a regular tetrahedron has 4 faces labeled 1 to 4. So it has 4 faces. So it has 1, 2, 4. So it's 1, 2, 3, 4. So I'm just doing that to think about it so I don't forget. A die is labeled 1 to 6. So it has 1, 2, 3, 4, 5, and 6. It says, an experiment is rolling the tetrahedron and record the number on its face down. Roll the die and record the number on its face up. So we're going to draw a tree diagram to list the possible outcomes. So I'm going to roll the tetrahedron first. So I'm going to put T for tetrahedron. And what are my four possible chances? Or four possible outcomes for my tetrahedron. I could have had a 1, 2, 3, or 4. So if I go like this, I could have had a 1, 2, 3, or 4. Then when I roll the die, I could have had a 1, 2, 3, 4, 5, or 6. So for each one of these now, I branch it off into 1, 2, 3, 4, 5, and 6. And I do the same for each one of these here. I branch it off into 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And then finally, when I want to find out what my outcomes are, or what I could have gotten, I just go, okay, that's a 1 and a 1. So 1 and 1. Then it's a 1 and a 2, 1 and a 2, and so on. And I keep listing them out for all of them, and I should end up with, I believe, 24 possible outcomes, because there'll be 6 for each one of these. When I'm done that, I look back at my question. There we go. I look back at my question and said, what's the possibility of, or probability of rolling 2 even numbers? So looking back at what we just made, we'd see 2 even numbers. Well, none of these are even because this one starts with a 1. So I'd have to look at 2 and 2. That's one even number. Both of them are even. Then I'd keep going down through it and seeing how many of them were both even. And then I'd write that out of 24 possibilities. How many were even out of 24? So it's kind of like the one previous. The only difference is we had a few more possibilities or choices, outcomes that we could have gotten for this one. And just to see the answers, what it should have looked like in the very end here. There we go. So I'll zoom in a little bit. Let's zoom in there we go. So looking at these ones here, this is what it would have looked like. Just like we said, we've got our tetrahedron, and we've got 4 possible outcomes right there. And then for each one, for our die or our number cube, whatever you want to call it, we had 6 more possible outcomes. So if I had to go ahead and redraw the whole thing, I would have ended up with something like this. And in the previous question, I already did this one, as you can see. And this is what you would have ended up. This is what I drew. Now they put start here at the beginning. Okay, but most of the time you don't see that part. You just see your 4 possible outcomes. We only wrote down V, Y, R, and B for our first one.